some of the notation we'll use in this class, or scientific notation people use. Basically is 123, just 1, 2, 3 like we do normal mathematics. But then we also need to sometimes clarify between different bases, so we write either 10 in subscript, so I want to say this is so subscript 10 on that. Or we can just write the letter 10 underneath there. Also another way is to write homework. Yeah. Or we do machine or programming. We do.
Is that a D? 1, 2, 3?
Yeah. 1, 2, 3 D. These are all all subscripts. I want to say all these symbols are subscripts. And we use the pound sign. 1, 2, 3. To denote a number in base 10. We have this notion of weighted position. If I take this number, 123, we know it's 123 by the fact that we know that this 1 is in the what place? Hundreds place. So basically is, you go 10 to the second power, right? So we can denote the number as 1 times 10 to the second power is, 100. And then the same way with 2, we go 2 times 10, and it's in the first power, so we get 20. And then we have 3, which is in the 1's place, or 0th position. So 10 to the 0th power is 1, 3 times 1 is 3, 3. So if you can see what it is, if I add this up, you see that we got 123.
You can't say 3 times 1 to the 0?
Well, 10 to the 0th power is 1. So it's 3 times 1. It's the same thing as, we're just saying is that that's what we do it is. You think about it as this is the base, and this is the position.
Oh, so everything has to be 10.
Yeah.
Okay.
So that's how we define weighted position. So say is we're using base 10. So this is base 10. So we use the our base here is 10, and our power is the position. So this is say the 0th position, first position, and the second position of the number. So we have the power on the number. Right. How we added decimal numbers, right? So we know we do 1 times 1 plus 2 plus 3. So we have 2 plus 1 is 3, right? When we did this number, we realized, all right, I have 9, which is my last digit in base 10. I add 1 to it. I don't have any more digits to represent that number, right? So what we did is we went to grab the beginning digit, if you want to say, and then we carry it to the next power, 1, so we get 10. Another way is to look at it as we have a circle. Kind of like your odometer on your car. It keeps ticking down, going around and around. When you hit 0 again, the next cog or gear on your odometer will start clicking 1. So every time this goes around, this one docks down 1. So 1 full rotation, this one goes, we'll get 1 knock. Goes another rotation, next gear will get knocked 1. Same kind of notion we do with this is that I have 1, 9, I go here to 0, so that means the next power has to be 1, right? So we have that kind of notion of adding our decimal system, right? we'll go to base 2, binary, right? We have 2 digits, 0 and 1. These are known as bits. So 0 is a bit, 1 is a bit. The notation we use for binary, put the subscript 2 underneath there, or subscript B, or we do, this is a 0, B, so this is like the, you want to say when I did the pound sign on the decimal system, this is the same kind of notation there. So this part's the number, this is just telling me that this is binary. This is like for computer languages. You can also just go B, 0, 1, 0. And another one is a $sign, 0, 1, 0. That's the notation that we'll use in class to denote binary system. If you don't put these subscripts on your number, I'll assume decimal, right? And you should assume decimal too if I don't do it. So if you don't see any of these subscripts, you assume decimal.
Question.
Yeah.
For the second to last one, it says 0, B, 0, 1, 0. And the one under it is a B.
B. Yeah.
Because that looks like a 1.
Yeah.
Okay.
I like this for you.
Thank you.
Just to that's that for you. All right. Okay. So. So we first have this notion of, it's called sign magnitude. Okay, so in decimals, we can abbreviate DC. So we have 1, 2, 3, 7, right? So
No 5?
I'm just gonna stop there. I'm just gonna, that's fine. Alright. So in binary, same kind of thing, we go 0, but I'm gonna have, I'm gonna use 3 bits. I need 4, sorry. And then so we go 0, 0, 0, 1. What we do here is we use the same kind of notion we did in decimal system. So I keep adding 1 to a number, but I only have 2 digits, right? So then I go 0, I carry the 1, right? So I drop 1 down. So that means 2 is represented by 0, 0, 1, 0. Right? Same thing with 3, because now we have this number. I want to add 1 to it. 0 plus 1 is 1. Then we have 0. I want to say we add 1. Right. So 3 is represented by 0, 0, 1, 1. Okay. Well, we can kind of see the pattern we go here. So now we got to add 1 to this one, so it's going to be 1, 0, 0, 0. Add 1 to the 5. And 1 to that number, 6. And 7. It's that way. Right? So basically is, if I only used 2 bits to represent a number, I can only represent 0 and 1, right? If I use 2 bits to represent a number, I can represent only 0 to 3. Alright, hope you can see that, because if I only use 2 bits, if I add 1 to it, I get 0, 0. Okay. Because I don't have another, I'm only going to use 2 bits. So like in assignments and homework, when we do binary math, I'll tell you how many bits you have to represent a number. And so, that's that notion. Okay, how do we get a negative number? Right, in decimal, we always make negative like that, right? 47. A computer, we have to get a symbol or a value to this negative number. So basically what we did is we decided we want to make 1 our number for a negative number, right? So if I want to make a negative number, we're still using what's known as sign magnitude. I'm going to make the 1 as my sign. So if I want to say 0's here, it's a positive number. So if I go 1, 0, 0, you could start. We'll make that negative 0.
How would you differentiate that from 8?
8, that's what I said before. It's how many bits I tell you have. How many bits you have. Like here, I have 4 bits. Makes sense?
Right.
So,
So you say the first bit is going to be my design.
yeah. So the most significant bit, what we call it, or the highest bit in the number is if it says signed. All right, because you can have unsigned and signed values. All right, so if it's signed, the 1, the most significant bit, will be 1 or 0, you know, if it's negative or positive. All right, so in sign magnitude, we say, okay, this is 0, 0, just like up here, we have 0, 0, 0, 0, right?
I guess I'm a little confused because in IP version 4, you know, like when you have like, you can not get a negative number. So I guess I don't understand that first leading bit.
It's in
It's-
IP4, it's unsigned.
So you're saying we have 4 bits.
Yeah, this is
First
going to
one's
be,
denoted, I guess the first one's the sign of whether it's negative or positive.
yeah.
I guess that just doesn't make sense. It blows my mind, I guess.
Yeah, well,
Just from what I understand of binary, but I don't know. Maybe I
So
don't
if you have
understand.
4 bits, you really only have
yeah,
three bits.
it's basically, we have these 3 bits.
So that's only in this right here with sign? Oh, that's only in sign or something? What's
Yeah.
sign, I guess? Sign
Yeah.
is just this form of
Yeah,
understanding binary?
yeah.
Okay.
So, unsigned, basically I want to win.
All right, I'll just, yeah, that's what I needed in sign.
Okay, yeah. If you
So
wanna think about
0
it,
is positive and 1 is negative.
yeah. So 0 is positive, so I can say like 7 is represented by 0, 1, 1, 1. And this is in sign magnitude, right?
So if you wanted to do negative 47 like that, you'd write out 47 in binary and then throw a 1 in front of it?
Mm-hmm. In sign magnitude.
Right.
Sign magnitude.
So if it's not sign magnitude, that would be 8.
Then you're adding a bit.
Yeah,
in into this.
if this was not sign magnitude, if this was, let's go, I'm gonna erase this part. Since that is signed, I'll do unsigned over here. Let's go like this, make sure we clarify this. Okay, so I'm just gonna do 3, okay? Hopefully we see the same kind of pattern evolving.
So if you do negatives,
Yeah, as I said, this is what we do here. Negative,
why
basically use the most significant bit, we make it 0 or 1.
Right,
If 0 is positive.
understand that, I meant unsigned.
Unsigned, it can't be negative.
Okay.
So,
It should be technically 4 because you clarified 4 bits at the top, right?
Yeah.
So you should have 4 zeros actually, right?
yeah,
Sorry, it's just part of this.
yeah. No, that's good. Sorry. I just try to make it more easier for me to write.
Yeah.
5. So 7 in 3 bits, unsigned, 7 is the highest we can represent in an unsigned 3-bit in binary, right? If I do, I'll do the 4 bits. So we can get so what's the highest number we can represent in binary? 16, we got to count for 0, so it's 15. So what we want to say is, using base 10, base 2, binary, I have 4 bits, so I can represent 16, but you have to count for the 0, so 15 is the highest number I can represent, so this is 15, 14, 15, so on. Okay, so this is unsigned, right? Basically is I just keep adding bits on, I can represent bigger and bigger positive numbers, right? Basically, if I, in a problem, it will say signed or unsigned, right? So that's how we do unsigned numbers. But when we want signed numbers, the first way is sign magnitude, right? And all we did was basically, if you see what we did here, all we did was add sign bit on there. So we lost some ability to represent, can't represent 15 anymore because now I'm using that 1 bit for a sign bit. So now I can only go to negative 7. So now I get negative 1 here, negative 2, 3, so you can see in sign magnitude that all we did was add the U1 to it, right? So if I add 3 and I want to subtract 3 from it, so I got 3 is 1, 0, 1, 0, right? And then so basically I'm going to add these two numbers together. So I'm going to add negative, I'm going to add 3 plus negative 3, which is basically 3 minus 3, right? So which number should I get?
0, 0, 0, 0.
So I get 1, 1, 1 plus 1 is 0, carry the 1, 1 plus 1, 3, we get 1, carry 1. Well, 0 plus 0 plus 1 is 1, I get 1, I get negative 6.
So you took 3 and you minus 3?
No, I went, sorry, best way is 3 plus negative 3.
That defies like math and
It does defy math.
What's wrong?
It's wrong. Can't do it that way, right? No.
Yeah, exactly.
Yep. So we had to create another way to represent numbers, okay? Because we can't do addition. We can represent a number, negative or positive, with sign magnitude. We can't do any addition. We can't do any arithmetic with it.
So I shouldn't remember that.
Basically,
Yeah.
basically, I want you just to know is what is wrong or what is the difference between. We're going to talk about 2 more different ways of representing numbers, and the last way is the right way. All right.
Okay.
So the first one we call 1's complement. Alright? I was going to leave it to 1. If you look at page 24 in the book, you'll see the exact same table, actually a little more bits than I am. So, yeah, page 24 in the book. So we're going to do the same notion is, we're going to use this as a sign. The last bit is the sign bit. So these, the positive numbers are all the same.
What does this ones mean?
Yeah, it's called one's complement.
What does it mean?
It's just what they give the name of this type of representation of binary numbers. Alright, so we also want to know is we also wasted a digit. I mean, what's the difference between -0 and 0, right? My table is off. That's what happens when you don't use a grid whiteboard, right? Alright. So what we're going to do instead is I'm going to take the number 0 here, and we're going to basically is flip the bits. So what was 0 is now 1. So now -0 is going to be 1, 1, 1, 1, 1. So I'm going to go this way as 1, 1, 1, 1 is 2. Right? So then we're going to take 1, and we're going to flip the bits again. So it was 1, now it's 0. It's 0, now it's 1. Right. So now -1 is 1, 1, 1, 1, 0. And then we keep going down, take 2, want to do the same thing, and we're going to not at all, so we're going to get 1, 1, 0, 1. We're going to get 0, 1, 1, 0, 0. And we're going to get 1, 0, 1, 1. And I'm sorry it's not maybe lining up correctly, but it's kind of hard to. 1, 0, 0, 1, and then it's 1, 0, 0. So -7 now is negative, is 0, 1, 0, 0, 0. Alright. If you want to look at it is, I go back to the wheel. I have 0, 0, 0 up here, and 0, 0, 0, 1, 0, 0, 1, 1. Need more room. All right.
So there's more than one way to represent negative numbers.
Yeah. That's basically what we're showing here. Basically, the first way was we added the negative, just put 1 in front of the number. And here we're like, we can't do arithmetic here with sign magnitude, so we had to create a different notation. we want to think of it that way, yeah. Mine is more like I added 3 to -3 and I got -6.
Which doesn't,
It doesn't make any sense, so,
Well, yeah, but it would make sense to do 3 plus 3 times -1, right? Which would be -6. So, like I said, you're going against the Lewis operation, you're doing the Lewis operation incorrectly. Which is what you think. 3 plus 3 times -1 is -6, which is why you get -6.
Where's the timesing coming from?
yeah,
It's
there's no,
from the one at the beginning, because 1 is equal to a -1. So,
And
1,
there's no-
-1,
but when I add a 3 to -3, I don't do anything else, I just add 2 numbers together, right? I just add.
yeah, but you're doing the addition before you do
it's the way the computer would do it, because the computer would do the 3 plus 3
If you
first.
then inverse it.
No, the computer just did what I did. It's gonna take these 4 bits and it's gonna add them together.
We haven't even programmed the computer to do multiplication yet, we're just
Yeah,
talking about bits.
yeah.
Right.
I'm just added these bits numbers together. There's no multiplication in it at all. Yeah. So this is what? -7? 6, 5.
Yeah, the book has it with 5 bits instead of 4.
Yeah. Like I said, it doesn't. It's the same kind of philosophy. Just this gets bigger. I just trying to make it more faster for me to write it. -1, -0. All right. Hopefully, you can see is we get redundancy again. We get 2 numbers represent a negative number. So I'm going to do the same thing we did again. So we got 0, 0, 1, 1, and 1, 1, 0, 0. So man, just add them together. So I'm going to get 1, 1, 1, 1. So get -0. This is 3, that. What I say. So now we got mathematics, right?
So basically, if you want to do arithmetic with binary numbers, you flip the bits on the negative number and then add them together.
One more
So
step.
One's complement.
Yeah, this is for 1's complement.
Now, in 2 complement.
Yeah. 2's complement. So basically so the difference between sine magnitude 1 is, what is the difference?
With the bits.
You can't add.
Yeah, you can't do basically mathematics. We can represent the number, we can't do math with it. 1's complement, we can do the math, but we get this redundancy. Basically is we get
So like depending on how many bits we have, we'll eventually go back to like.
yeah, that's why I always think of a circle and write out your bits like a circle. And so you can see, keep adding 1, if you notice I keep adding 1 to this circle. And then you always keep going around like this. I'm not going to get a 2's complement. Read over again, or come see me and I can explain this more if you want. But we'll go again on start for 2's complement, the way computers are actually built, the way we do things.
We have homework.
I didn't check. I would make sure you check. Yeah, check the schedule.